Okay then, so this is Dr. Ruth Callaway. She is also from Swansea University with the SEACAMS project, and over the last couple of years has been working with SALIX on looking at rock rolls and how they might be used to enhance some of our bank protection.
Thank you. Thank you very much. Good afternoon, everyone. I think this is sort of the last of rounding off the afternoon session, and I think it is a very positive story about a product which is sort of conceptually quite simple and intuitive, but remarkably effective. So I want to talk to you about rock rolls and how they interact with freshwater and marine systems, and specifically I want to look at how rock rolls impact biodiversity. Now, when you come to a river or to the coast, you may be greeted by these hard engineering structures, by sheet piling or riprap, or my background is marine ecology, so I particularly like these massive concrete tetrapods that you might find. And all these structures have one thing in common. They are very effective in separating a water body from terrestrial land and prevent flooding and erosion. And that may be necessary if, say, for example, life is at risk. But the price you pay for using these hard engineering structures is great, because you prevent a whole plethora of ecosystem services. For example, they don't add an awful lot to the cultural values, to the aesthetic and recreation. They prohibit processes that might improve water quality. And they certainly don't do an awful lot for habitat creation, for wildlife, for fish, for example. And they certainly don't do an awful lot for biodiversity. And biodiversity is more and more recognized as an extremely important feature of all our ecosystems, just for sustainability and their ecosystem resilience. Now the question is whether we can engineer coasts, riverbanks, coastal defense structures in a way that they promote or restore or protect biodiversity. And this is just sort of an image that a screen grab that was last year on the BBC webpage, where some scientists from Australia, they had just drilled a few sort of flower pot type structures to a harbour wall, thereby creating artificial rock pools and boosted biodiversity. So a very simple measure. I actually think you can probably do a lot better. But there is, and we've seen actually a lot of examples today, there is an increasing body of knowledge to say, well, you can actually engineer biodiversity if you put your mind to it. And on the other hand, there is more and more legislation that has sort of biodiversity at its heart, if you like. There is the Natural Environment and Rural Communities Act in Wales now, so we are from Swansea. They are just passing a bill that has a very, or will have a very powerful biodiversity legislation. NRW, the equivalent to the Environment Agency in Wales, they are thinking already how they can prove that everything they do promotes or conserves biodiversity. And a lot of the European legislation we have also sort of focuses very strongly on biodiversity. So on the one hand, we have sort of the scientific knowledge that it can work. On the other hand, we have the legislation. And the challenging bit is the middle bit now, is how do we actually do this? And I think that is where rock rolls could play a major role. Rock rolls are essentially simply big mesh bags filled with material, generally smaller stones or larger stones. They are placed in areas where, like in erosion-prone riverbanks, and then over time, with sedimentation, they become part of the riverbank. And my colleagues, actually, so Ian Dodkins and Anushka Menzel, they did a project last year with SEACAMS to look at what do rock rolls really do for biodiversity, and how does it matter what kind of stone size you use. And in order to find that out, they took a small stream in Wales and placed rock rolls with different size stones, small stones and large stones, beside riprap, and then sampled that after 3 months. And they looked primarily for the invertebrate diversity in those rock rolls. They found mostly insect larvae and small crustacea, river snails and freshwater snails, all very good food sources for amphibians and fish. And they looked at the diversity, the biodiversity in those rock rolls. And here on the left-hand side, you see just the abundance, so of the sheer number of animals, invertebrates found, and on the right-hand side is diversity actually in terms of species richness, the number of species they found in them. And they took, the first column is kick samples, then small stones, large stones, and on the right-hand side is riprap. And they found that just the sheer numbers of animals they found was significantly higher in the rock rolls. They were about 3 times higher than in riprap or the kick samples. However, there wasn't much of a difference between the different stone sizes, so small or large stones, that didn't really matter. The species numbers, the numbers of species, you find a somewhat similar pattern. The mean number of species was slightly lower in the riprap, certainly lower in the kick samples, but statistically, actually, there wasn't a significant difference between the rock rolls and the riprap. So the key message they took away from this was that what rock rolls do first and foremost is they increase the number of animals, the habitat for animals that can live in the riverbanks. They also looked at the amount of sediment that was trapped and found that it was 50 times higher in the rock rolls compared with the riprap. And that is, that may explain partly, or maybe certainly linked to the invertebrates and the pattern that they found in the invertebrates. Now, obviously, this was just after 3 months, and we have to be careful to interpret this, and we can't be too generic about these results. This is just a snapshot in time. The impact of rock rolls will certainly change over time, but it gives a first understanding of what rock rolls do to biodiversity in river systems. Now, so I saw what they were doing in rivers, and as a marine ecologist, I thought, well, actually there's no reason why rock rolls can't work in the marine environment as well, because in the marine environment we also have reef-type structures. We have oyster banks, we have mussel banks, we have tube worm reefs, and all of those reef-type structures are protected features under the Habitat Directive, and they are protected because we know they form oases, small areas, reefs that have a different and often a much more diverse fauna than, say, all the sand flats and mud flats around. So we thought we'd do some experiments to see whether we can artificially create some of those reefs. And the SEACAMS provided us with mini rock rolls, made that for this experiment, and we created other reef types, or reef bags as we call them, with shell material, so with mussel shells, with cockle shells, and with oyster shells. And we put them out into Swansea Bay created a number of replicates, distributing them all around the bay, and looked how they were colonized. And after 5 months, we look at what we were finding in them, and in the marine environment, you find more polychaete worms in those, or in the marine environment in general, and so we found them also in those bags, and also small crustacea, amphipods, isopods, and shore crabs. And if you look at the diversity in those, the four first columns are the different reef bag types, so the cockle shells, mussel shells, oyster shells, and then the actual rock rolls. And the fifth one at the end is the fauna that you find actually in sand as a control, just. And all of those reef bag types promoted the number of species you would find. There was always a significant difference. And in fact, the stone bags, the rock rolls, had the highest numbers of species of all the different versions that we had created. And a similar pattern was for the abundances, so for the sheer number of animals in there, again, more than in sand alone, so any reef type structure will promote the abundance, but in the stone rock rolls we had about 10 times more animals than in the sand, and also significantly more than in some of the shell types. Well, when I started that experiment, I thought that probably a defining factor would be how much sediment was trapped in each of those different types, because most of the species are benthic species, and they need to bury in sand. They are dependent on sediments to some degree. And there was a difference between the amount of sediment trapped, although the variation was between the different replicates was so high that statistically there wasn't really much in it. But also, if you did a regression analysis, the amount of sediment didn't actually explain the changes in diversity at all. And the factor that best explained the changes in diversity was the amount of interstitial space that each of those materials provided. So the more space there was between the materials, the higher the biodiversity. And rock rolls, for example, provide a lot more space, interstitial space, than, say, small cockle shells. Now, I guess it's this relationship, this correlation, you cannot extrapolate that, because then, something like tetrapods, which provide a phenomenal amount of space, would be extremely biodiverse, which they aren't. So the relationship is probably something that is going to increase, then probably petering off and then going down again. But that would be something to find out, so what is the ideal interstitial space that material can provide for the maximum biodiversity. So again, perhaps, as mentioned before, that was just a snapshot, and it was only in Swansea Bay, a very small experiment, but it did we started to understand what these rock rolls do in the environment, and we could certainly show that they would increase biodiversity generally. So in summary, riverbank and coastal engineering increasingly demands solutions that protect and promote biodiversity. And I think rock rolls offer an engineering design that enhances biodiversity in freshwater and coastal ecosystems. The rock rolls provided habitat for invertebrates, increasing numbers 3 to 10 times. In rivers, rock rolls accumulated 50 times more sediment than riprap. And in the coastal environment, the availability of interstitial space promotes invertebrate diversity. Now, what's next? Next for us is certainly to understand better the impact of rock walls on biodiversity over time, how that changes. Then we want to know more about the site dependence of these effects and already find out assess the site independent characteristics of rock walls. And then there is no reason to only use small or large stones. You can use all sorts of material, and we want to experiment with that. And I guess the ultimate goal has to be to develop some sort of predictive model that you can go to Natural Resources Wales or the Environment Agency and say, well, if you were to put a rock wall into this environment, that would increase biodiversity by X%, and you would most likely attract these and these many species and this type of fauna. We're still a long way away from that, but given sort of the first experiments we've done, I think it is a perfectly reasonable aspiration to have. That's it. Thank you very much.